Today, this evening, as usual on Thursday night, we have a lecture as a part of activity of Academic Astronomical Society Rijeka, and tonight's guest will be our friend and colleague from Centro Studi Astronomici Trieste, Margini. And why we have invited him for this particular evening, for this particular topic, because Ivo and I, about a month ago, were at Friuli Venezia Giulia Star Party, which was at the beginning of September, and he also Mark also had a presentation about exoplanets and planetary migration, which was really interesting presentation to me, because I learned something new, why hot Jupiters can also appear very close to their parent stars, which was kind of mystery to me. How could it happen? So Marco is our friend from Trieste, but he was actually doing his PhD, and he's in his very last stages right now of his PhD. He has graduated at the University of Padua, his master's degree at the astronomy astrophysics, and the topic was exoplanet, if I remember well. But now for his PhD, he has enrolled in Electra synchrotron in Trieste, in Bazovica near Trieste. And his topic was radio wrangling, I believe, and not pictography, but what's the
Tychography.
Tychography. Thank you. X-rays. Yes, X-rays. Okay, Marco, apart from his scientific and research projects, he is also, as he mentioned in his CV, he is an amateur astronomer, he's been amateur astronomer for all of his life, and he says that when he became a member of astronomical studies on Trieste, astronomy became his full-time hobby. So let's start with our presentation. Marco, the floor is yours.
Yeah, welcome everybody. Thank you for being here. This is the perfect evening because it's raining outside and it's really cozy, and we are here to learn something about planetary astrophysics. So, yes, I will talk about the formation and also the migration, as Lovro said. So the presentation will be divided in two parts. First, I will explain how a planetary system is formed, basically, and then we will have a look at the possible migration path that planets can undergo, and then we will have a look at the consequences of these migrations. First of all, we need a star. In order to have a planetary system, we need first a star. How are stars formed? I will go very quick in this part, so it would there would be a complete lecture about star formation, but I will go very fast. So in the universe we have these gigantic gas clouds. They are made of hydrogen and helium mostly, but they also contain other heavier elements. Which come from the supernovae explosions, okay, and some recycled material from other clouds. So it's a mix of materials, mostly gas, but there is also a tiny percentage of dust, of heavy elements. So when the gravitational collapse begins, you can see the formation of these structures, very well-known pillars of creation, where the gas basically collapses, so it forms these denser agglomerates and high-density regions. And then there is a critical mass called the Jeans mass. This is the only formula I will show you, I promise. And so if the mass is bigger than this mass, then the cloud can collapse and form a star, a new star. And then there are a lot of things going on, stellar winds, supernovae explosions, and everything can halt the process of star formation. When you have a cloud, only a part of it will actually collapse and give rise to a new star, but most of it will be blown away by these events okay, before more stars can be born. Okay, and then, yeah, this is, okay, another detail of high density regions. And then we focus on one of these clouds, okay, which is collapsing. And for the conservation of the angular momentum, you have that around the newborn star, a new protoplanetary disk is formed, okay, because the gas is not steady. The gas is always moving in the universe. It has always some velocity, always. And when it collapses, it becomes smaller, and for the conservation of angular momentum, it becomes faster, okay? So it starts to rotate around the newborn star, and this is why we have the disks around the stars. And the whole process of collapse and disk formation takes about 1 million years. Okay, I will show you many time scales in this presentation, like this. This is to be intended very rough, okay? This is an order of magnitude. It can be 800,000 years, it can be 1 million, 2 million, 3 million. It's the order of magnitude, okay? It's not precise, of course. So now we have a disk, and we want to see the characteristics of this disk. For example, first of all, the composition. It's made of gas, as I said, but since now the disk can cool down a little bit, it's not hot like a star, it's cooler. So we can have molecular gas, other than ionized gas, of course, in the center. And then we have heavy elements and dust, as I said. Dust is a collection of heavy elements at the end, no? Dirt, we could say, in other words. This disk has a very complex structure, okay, we believe. There is, first of all, a gap in the middle, close to the star. This is the region where the stellar winds are very powerful, and there is also the magnetic influence of the star. And this gap can be, roughly speaking, 0.1 astronomical units. And in this gap, the planetary formation is forbidden. Nothing happens here. There is only some material that is about to fall on the star itself. So there is no planetary formation here. And the total radius of this disk is about 50 astronomical units on average, but it can be even much, much more. And the thickness is also variable depending on the distance. So it can be thicker farther away from the star. And then now we have a look at also in more detail about these processes that happen inside the disk. Okay. First of all, there is a very important concept that I need to explain, which is called the snow lines, or frost lines also, in some cases. It's a very important concept, and we will see why. These lines, which are actually rings because they set a distance from the star, so for the circular symmetry of the system, these are rings actually. But we are looking here at one-dimensional model, let's say, so they are called line for this reason. Basically, any molecule, any compound has a snow line, has a frost line. There is the snow line of the water, which says, okay, on the left of this line, I don't have water, like the molecule itself doesn't form because it's too hot for the hydrogen and oxygen to go together, okay? And on the right of this line, I do have snow, I do have water, which in vacuum is in the form of snow and ice, never liquid, okay? But it's still water, okay? I only have water on the right of this snow line. And this holds for a lot of compounds, not only water, also CO2, carbon dioxide as its snow line. The water snow line is about when at the beginning of the planetary formation, it is around 3 astronomical units. Depends the model you use, but around 3 astronomical units. So basically where the asteroid belt is nowadays. While the CO2 is around 9 astronomical units, the frost line of CO2. So that means we have CO2 ice on the right, and we don't have CO2 on the left. And then there are also other compounds like methane and carbon monoxide, which are the snow lines related to these elements are even farther away, close to where Neptune and Uranus are today. So this means that the heavier compounds, molecules, can form closer to the sun, okay, because they have a higher temperature of formation, while lighter compounds can form only farther away from the sun, okay. And so there is this sort of stratification of the chemical composition. All the processes that I will describe now of planetary formation have to happen in the first 3 to 5 million years after the formation of the new star, because then after that time, more or less, it happened the dissipation of the disk because of the stellar winds and all these processes. The remaining gas, which didn't lead to the formation of a new planet, is blown away. So the planets have a limited time to form, only a few million years. If they don't form in this time, it's too late. Okay. Okay. So let's go through the steps of planet formation now. First, you start from the dust. The dust is about 1 micron in diameter, in size, okay? And it can grow very quickly in about 1,000 years, which is very quick, to a size of about 10 centimeters, which are called pebbles in English, okay? This size, the rocks this size are called pebbles, and in this process, the gas is really, there is a lot of gas still because we are in the very beginning, and the interaction with the gas is very important in this step, and the forces that are responsible mostly of the formation of these pebbles are van der Waals forces. Van der Waals is a very broad name which describes a set of forces. It's basically forces that have to do with molecules and hydrogen bonds and small stuff, basically. No, I will not go into the details, but they are forces that like keep together molecules and small particles, I would say, okay? And also, there is another effect that we suppose that is very important, which is turbulence, because when these pebbles fly in the gas and dust cloud, they create turbulence, they create flows of gas, and this turbulence makes some swirls like wind, you know, when the wind blows and it forms some pile of leaves on the ground. The leaves are first evenly distributed, and then the wind comes, and then some piles are formed because of the turbulence. And this is supposedly very important for the formation of the very first bricks of the planetary system. And then the next step is from 10 centimeters to 100 meters, more or less. This is also very rough. And it's called the 1 meter barrier, the 1 meter problem. For many, many years, the scientists, the astronomers, tried to think which kind of process could overcome this barrier, because gravity is still too weak. The pebbles here, the rocks, are too small to be attracted together by gravity. So gravity is out of the play, out of the game. And if you think about it, there are not many options. In physics, there are 4 fundamental forces. 2 of them act at a very small distance at the atomic level, so they are not our candidate. And if you rule out gravity, the only one left is electromagnetism. So in this case, electrostatic forces. And indeed, this is our theory now. We think that the 1 meter barrier is overcome because of electrostatic forces. The pebbles hit each other, they charge each other with the heating, and they also charge with the gas, with the friction in the gas cloud. Passing through the gas cloud, they collect some electric charges, okay? And they stick together because of electrostatic forces. And also, I must say that the friction with the gas is still very important, because in order for the electrostatic forces to win, the impacts between the rocks must be very slow, because if it is like a bullet hitting a rock, then it will disgregate. But if the impact is slow, then the electric forces can win. So the friction is important, because the rocks that go faster are slowed down by the friction. So since the friction with the gas is directly proportional to the velocity, the fastest rocks are the ones that are slowed the most. So at the end of the day, you have a uniform velocity because of the friction. So this is very important. Then after that, you have a very quick growth. It's called the runaway growth, which means very fast, basically. I would say exponential, because now your gravity comes into play after more or less the 100 meter step. And now this step is very quick, only 10,000 years, because there is a lot of rocks now. The disk is full of rocks, and the interactions are in the order of the day. Every day there is an impact, and so this growth is very, very fast. And here I put an example. This is the comet that was visited by the Rosetta mission, and you can clearly see that this is the result of a very slow impact between 2 bodies that just touched and stayed together because of gravity. Their gravity is very weak, but it's enough to keep them together. And this is what's happening now. The impacts are very slow, and the bodies stick together because they are loose. They are a collection of rocks and boulders, and they are loose. They are loosely connected. So when they impact, they can deform and accommodate the impact itself. No? So they stick together. This is very efficient. An efficient way of growing, okay? And these bodies now, about 100 kilometers in size, are called planetesimals, okay? After the planetesimals, we have the protoplanets formation, which are bodies a little bit bigger, of the order of 1,000 kilometers in size. And this is the size of the nowadays dwarf planets. The dwarf planets that we have today are the remnants of this phase of this protoplanets formation. Okay, this is slower. This takes 100,000 years on average because there is less and less bodies in the planetary system. So the impacts are more rare in this growth, which is called oligarchic growth, because there are bigger bodies. The first bigger bodies are formed, and the bigger bodies attract to themselves the smaller ones. So that's why it's called oligarchic, because the bigger you are, the more bodies you can pull towards you, and the bigger you become, etc., etc. So they create their sphere of influence. Last step is the actual planetary formation. This is very slow because the impacts are very rare, because there are only a few tenths of these bodies in the inner solar system, for example. So the impacts are very, very rare, and it takes 10 million years. And this leads to the formation of rocky planets, and this is the phase where it's thought that the Earth had the famous giant impact, you know, the impact that gave rise to the moon. The main theory, if you don't know, is that the moon was formed when two of these protoplanets collide, and in the impact, a portion of the crust of one of them is ejected in the space, and then the moon is formed. So this is the era, the epoch in which the moon is formed. And yes, the theory that we have now is that the Earth underwent maybe 10 or 12 impacts of this size. One of them gave rise to the moon. So this is the theory that we have. And then another, okay, if we are talking about rocky planets, that's it. That's the end. But if we are talking about gaseous planets, there is another step on top of this. So everything I said until now is still valid for gaseous planets, but then they need to build the gaseous envelope, which takes more time. And in order to have to attract the gas, the core, the planet has to have a rocky core. And this has to be at least 5 terrestrial masses, let's say more or less. If it's too small, then it doesn't attract the gas. It's not, the gravity is not enough to attract enough gas, and it doesn't become a giant planet. But if it is above this limit, then it can attract the gas and form these clouds and these clumps, and then inject even more gas and more gas. And this is a very rapid growth. And this has to happen in the first million years. Otherwise, then, as I said, the gas in the protoplanetary disk is swept by the stellar winds, so no more giant planets. And this formation is also very restricted to an area which is about 5 to 10 astronomical units. Because if it is closer, there is not enough material to build a core of 5 terrestrial masses. There is not enough material if you go closer to the star. If you go farther from the star than 10 astronomical units, then you have the opposite problem. The spaces are very large, and the impacts are not fast enough to build a core of 5 terrestrial masses in time before the gas is swept away by the star. So where you have a very strict area here. Okay. And this is about everything about the planetary formation. Okay. By the way, if you have questions, you can interrupt or keep them for the end. Now we can talk about the migration. So if you didn't know, humans are not the only thing that can migrate. Also planets can. And it's very interesting to see the outcomes of these migrations. So let's begin with the second part. There are two types of migrations. Let's say the ones that are driven by non-gravitational forces, and which I will explain first, and then the ones that are related to gravitational forces, which I will explain later. So first of all, type 1 migration of non-gravitational forces. It's a quite fast path, I would say, because it's only 100,000 years. So if it is shorter than the average life of a protoplanetary disk, which is 3 to 5 million years, then it's considered to be fast. Just to give you some reference. In this kind of migration, there is a strong interaction between the newborn planet and the gas disk, gas and dust. While the planet goes around the star, these wakes, which are standing waves basically, of gas are formed, which can spiral towards the star. And since the wakes are asymmetrical, the one which is outside is usually bigger and the one inside is smaller. This can lead to a non-zero force on the planet, okay, of drag and friction, etc. And this kind of migration is usually, but not always, followed by an inward migration. So the planet goes inwards towards the star, usually, but not always. The most important detail is that this path, let's say, is true for planets between 10 and 20 terrestrial masses. If it's too low, it doesn't create enough wakes to do this. So we need at least 10 masses. If the planet is bigger, then we have the type 2, which is for planets bigger than 20 terrestrial masses. This is different from the first one. This one on the left is the type 1. This one on the right is type 2. The difference is very clear. In the type 2, the planet is so massive that it creates a hole in the disk. There is an empty ring around the star created by the planet. And this changes a little bit the models and the forces into play, but the result is very similar. These two types are very, very similar. Just one is for medium planets and the other one is for big planets, but they are very, very similar. And this is also faster. It's only 10,000 years as an order of magnitude. And it's also mostly inward, okay? Then we can have a look at the gravitational driven migration. The first one is, of course, scattering. Scattering between two planets can happen at any time. Can happen in the first parts of the planetary formation, but it can also happen late in the formation after the disk has dissipated. It doesn't matter. Two planets can always pass very close one to the other, two protoplanets or whatever, and in these cases their orbit is heavily perturbed, and usually one of them doesn't survive in these very close approaches, because either it is sent on the star, and so it's swallowed by the star itself, or it is ejected by the system and it starts cosmos. While the other one that survives can change very heavily, abruptly, I would say, the orbit. It can go in a very close orbit around the star, or in a much wider orbit around the star. So this type of migration is very, it's rare, I would say, because it needs two planets to go very close one to the other, but it's very efficient. And then there is another type of migration which is called the lead of Kozai. This image is AI created, because I couldn't find a better image on the internet for this type of resonances, because they are already quite rare and they are only known by the specialists. And then on the internet you don't find any source. So I kind of like this this image, because these lines give the perspective of something geometrical. And indeed, these resonances has to do with the inclination and the eccentricity of the orbits, which are the geometric parameters of the planets. No? So in this case, if you have two planets in orbit around the star, one star, which doesn't share the same plane, so their inclination is a bit different, let's say 10-20 degrees difference between the two orbits, they can interact, they can go into this kind of resonance where they exchange their eccentricity and inclination. So for instance, if in one period, or in one epoch, let's say, one planet has a high eccentricity and low inclination, the other one has a high inclination and low eccentricity, they can go into this resonance and exchange energy through this resonance, and the one that had the low inclination will become will have a high inclination and a low eccentricity, and vice versa for the other. So they go into this dance, okay, we could say that, and there is this oscillation between inclination and eccentricity. And this usually, the outcome of this is always an inward migration, because the one that is closer to the star, when how can I say, the one that is closer to the star, when it has a high eccentricity orbit, it means that it goes very, very close to the star, no? Because when in the perihelion or periastron, the distance between the planet and the star is very small, so it means that the planet goes very, very close. And in these cases, this is not enough to explain the inward migration. We need another ingredient. The other ingredient is the tidal forces. When the planet is very close to the star, because of lead of Kozai resonances, or even the scattering that we saw before, or whatever other migration path that I told you, in these cases we have the gravitational, the tidal forces that take over, okay, and they can circularize the orbit. Because why? Because the planet, there is an exchange of energy between the planet and the star via the gravitational forces, and the planet is accelerated when it's closer to the star, and this modifies the shape of the orbit, which orbit after orbit it becomes circular. That's why we talk about circularization. So all the other, let's say, migrations that I told you can have as an outcome the fact that a planet goes very close to the star. But this is not enough. Usually, tidal forces are coming into play afterwards, and they can stabilize the orbit and circularize the orbit. So they are needed to have a stable outcome. Otherwise, the planet can fall on the star or have another fate. Okay, so these tidal forces always come after the other migrations that I explained. So now, finally, maybe the most interesting part for everybody, we will have a look in detail on, let's say, two main consequences of this migration that I explained. Okay, the first consequence is the late heavy bombardment. Maybe you have heard about this. This is the reason why we are here, because this is the event that brought the water on the Earth. Okay, so if we have water on the Earth, it's because of this late heavy bombardment. Because as I told you at the beginning, if you paid attention, the water snow line is at 3 astronomical units from the star, in this case from the sun. And the Earth is at 1 astronomical unit. So it's not possible that the water formed on the Earth from the beginning, okay? Because the Earth is closer to the sun than the water snow line. So the water must have came later. So we are very lucky. We are very lucky because of Jupiter and Saturn. They did the job. And now I will explain. So we can have a look at this graph. We have two graphs actually, one on top of the other. On the horizontal axis we have the time from 0 to 600,000 years. So the whole process of migration of Jupiter and Saturn took only about 500,000 years, because here it finished. And this happened in the first stages of planetary formation, which means about 3 to 5 million years after the formation of the Sun. So the gas disk was still there when this migration became started. Okay. So in these two plots we have the radius of the orbits in astronomical units here in this bottom graph, and the masses of the planets in this upper graph. And now we can have a look in detail. You can see that Jupiter is this line. It's already formed because its mass is constant, so it means it's already formed. It's already the mass that it has today. Okay, while Saturn is still forming. The mass of Saturn is still growing, you see. So Jupiter in this model, this is just a model, an hypothesis, because we will never have the 100% confirmation of this. It's just a theory, but it's the most accepted theory in the astronomical community. So that's why I'm telling to you. So Jupiter formed before Saturn, and it started a type 2 migration in the disk because of the friction with the gas disk. So you see its radius, Jupiter is this one, its radius is decreasing. This means that Jupiter is going towards the Sun, towards us, towards the Earth and Mars and Venus. Okay. Luckily, Jupiter would have done a mess, because Jupiter would have swallowed the Earth and Venus and everything else, because it was going to become a planet close to the Sun. because here is 0, 1, 2 astronomical units, 3, 4, 5. So it arrived to roughly 1.5 astronomical units, which is where Mars is today. So very close to us. But luckily, when Saturn finally was completely formed, he also started a migration very fast, much faster than Jupiter, and it caught up with Jupiter. It reached Jupiter around the 2 astronomical units, and this is actually why Jupiter didn't disrupt the whole inner solar system, because Saturn came to take Jupiter from the hood and push it back, because they went in a 3-to-2 resonance when they were here, and this halted the migration of Jupiter inwards, and they slowly started to migrate back. So if Jupiter didn't ruin the inner solar system, is because of Saturn came to take it, and because of the resonance. These numbers means that while Saturn was doing 2 orbits, Jupiter was doing 3 orbits. So this is the meaning when we talk about the resonance, is the ratio between the periods of the 2 orbits. In this case, 3-to-2 is the ratio. Okay. But this migration, okay, we are safe because Saturn took Jupiter away. But this migration had some consequences, of course. The consequence was that Jupiter and Saturn, while migrating inwards, they took a lot of asteroids and comets with them because of their gravity. They are very big planets, so with their gravity they do whatever they want. And that's why we had this late heavy bombardment, which refers to the fact that the comets, full of ice, full of water, came to the inner solar system because of this migration. And then a lot of impacts, we had a lot of impacts. So the comets full of ice coming from the outside of the solar system came in and impacted the Earth and brought the water on the Earth. And the Earth was the planet, among the others, that was able to keep it in the best way, because Mars was too small and he lost the atmosphere and much of his water. He still has some water, but not much because it's smaller. But while the Earth, it was perfect size and perfect atmosphere to keep the water, so we are lucky. And then, so this is why we have the water on the Earth. And this is also why Mars is much smaller than the Earth and Venus, because during this migration, probably Mars was still forming, was still small, was still a protoplanet, sorry. And this migration basically swept away every other planetesimal that was in the area. So Mars suddenly didn't have enough material to build up, to grow more. So that's why it stayed very small. And this is supposedly also why the asteroid belt between Mars and Jupiter is so small. The amount of material in the asteroid belt is only like 0.05% of the Earth mass. So it's not a lot of material, it's very low. And this is also, supposedly, this is also a consequence of this migration. So we have a theory, this is just a theory, but we already listed 3, let's say, outcomes that can be explained with this theory. So the more things a theory can explain, of course, the stronger the theory becomes. Because if this theory explains only one thing, and then it also brings in way more problems than the one that it solves, then it's not a good theory. But if the theory solves many problems without creating other problems, then it's a good theory. So we think that this is a good theory. And then there is also the fact of Neptune and Uranus. They are also caught in a resonance with Saturn and Jupiter. So while they are migrating, they are also caught in the same resonance, and they are also migrating outwards. Because as I said, all the planets must have formed between 5 and 10 astronomical units. All the gigantic planets, the giant planets. Jupiter migrated, so it probably formed around here, but yeah, more or less between 4, 5, and 10. This is, broadly speaking, the area that I told you before, no? And then the Neptune and Uranus also migrated to the place where we can find them today. Actually, they migrated more because Saturn, this graph is very short, but then they migrated more, and Saturn went to 9.5, Uranus went to 19 astronomical units, and Neptune to 30. So they migrated way more. But this is only short to show this behavior. Okay, so this is a very important, I will say, consequence of migration that we can explain. And the last one is the Lovros' favorite, the explanation of the existence of hot Jupiters. Hot Jupiters are very strange planets. They are Jupiter-like, so they have the mass of Jupiter, more or less, give or take, but they are very close to their host star. And this puzzled the scientists for years, because the very first exoplanet that has been discovered in 1995, almost 30 years ago, 51 Pegasi b, it was a hot Jupiter. It was a planet of the mass of Jupiter, orbiting at only 4 days around its star. So it took 4 days to go around the star. It means the year, not the day, the year of that planet, it was 4 days long, and they didn't know why. So after this, many more hot Jupiters have been discovered, and now we know what happened. So the planets clearly formed further away from the star, and then they migrated. How? We don't know case by case, but for sure it was mostly one of the migration paths that I showed you. So either a scattering or a lead of Kozai or a gas-driven migration, etc. One of these led to the formation of this class, I would say, this class of planets, which are called hot Jupiters. You see, this is the mass, so this is Earth masses. So Jupiter is about here. It's here, so yeah, about here. This is the mass of Jupiter. But you can see that the period in days, this is the orbital period, it's very short. This is 1 day. This is the 1 day line, this is 10. So between 1 and 10 days of orbital period, you can see this clump of this bump of planets that are discovered, and they can only be explained with the migration. There is no other explanation, because it's impossible for them to have formed so close to their star. So I think I said everything I wanted, so I would like to thank you for your attention.